Hello friends, in this video we are going to discuss application of a Schrodinger equation. This is the simplest application of Schrodinger equation. You can also call it as quantum mechanical treatment of translational motion in a particle in a box that is one dimensional. So every time in CSIR net question asks from this part, and these questions are very easy and you can easily solve this problem if you know the theory part from this portion. And I hope you will understand whatever we are going to discuss in this class. So without further delay, let us start with our topic. So in translational motion, we are going to discuss the free motion, that is motion of a translational motion of a free particle. So in order to describe that, we consider a one-dimensional box with dimension A. Okay, this is the dimension of the box A, and we consider a particle of mass m that is free to or allowed to move in x direction, and we also consider the inside the box the potential energy is 0. That is, inside the box all the energy is from kinetic energy of the particle, and outside the box it is infinity. Potential energy is infinity. We also consider in boundary condition that is the psi, whatever the wave function we use to describe this system, this quantum mechanical system, will be exist inside the box, but outside the box it will vanishes, it will not exist outside the box. This boundary condition we consider. So now the Schrodinger equation for such system we can write as d square dx square, since one dimension is considered, psi, this is the wave function of the system, and 8 pi square m h square e minus v psi equal to 0. We know that this potential energy is 0. So this can be written as d psi x square 8 pi square m h square e into psi. This portion we can write it as k square. Then the equation of Schrodinger for this system will be written as dx square k square psi equal to 0. We numbered it as equation number 1. We all know that this is a second order differential equation. The solution of this equation will be psi equal to root over 2 by a sine n pi by a into x. This is the normalized wave function for the particle for the system quantum mechanical system for particle in a one-dimensional box. So you should learn this formula. Okay, you should remember this. We numbered it as 2. Similarly, the value of energy can be written as nh square 8ma square, where n is the quantum number. Value of n can be 1 2 3 dot dot dot, and h is the Planck constant, where m is the mass of the body and a is the dimension of the one-dimensional box. So from this energy expression we can easily say that the energy of this particle is quantized, where in classical mechanics we got an continuous energy value, that is continuous spectra. So from the above discussion we have find the wave function, that is the normalized wave function for a translation motion of a particle in one dimension. Now we will discuss how the psi, that is the normalized wave function, will vary with x. Okay, two things. One is how psi, this will vary with x, and the probability of finding the particle, that is psi square, which is represented by psi square. This is the probability of finding the particle inside the one-dimensional box, vary with this dimension of the box. These two things we will discuss. First, consider the first one. So psi, for psi we know that where psi is equal to 0, we say that there is a node exists for the wave function. Okay, so for a node the psi has to be 0. For a one-dimensional box we can write psi equal to 0, that is a node is found where root over 2 by a sine n pi by a into x equal to 0. Okay, when this condition is satisfied, then there is a node for the wave functions. So this can be written as sine n pi by a into x equal to 0. So this is equal to n pi by a x equal to n equal to k into pi. The value of k will be from 0 to 1 to 3 to infinity. So from this you can write n pi into x k pi. So pi cancel out. What will have? X equal to k pi n into a. So this is the point where wave function will be 0 inside the box. So we'll see the different points where wave function will be 0 for different quantum number. Suppose for n equal to 1, x will be k a. That is, for k equal to 0, it is x equal to 0. When k equal to 1, x equal to a. That is, at x equal to 0 and at a, the wave function will be 0. That is, there is a node inside the box. When n equal to 2, x equal to ka by 2. That is, when k equal to 0, x equal to 0. When k equal to 1, it is a by x equal to a by 2, and it is when k equal to 2, then x equal to a. These are the 3 points where wave functions will be 0. Now we plot the graph of this one. how it will be the formula. So suppose this is the one-dimensional box. This side we have plotted the psi and this side is the x. For n equal to 1, we find that at 0 and a there is a node, so the wave function will be somewhat like this. Similarly, for n equal to 2, we find that there is a node in 0, a by 2 and a, so the wave function can be represented as this way. Similarly, we can also represent the wave function for n equal to 3, 4 and so on. Now we'll see the second graph, that is the probability versus x graph. If we see psi square, this is the probability of finding the particle inside the box. Okay, this probability will be 1 when the probability of finding the particle is maximum inside the box. So this p will be 1 when it is probability is maximum. For maximum probability, this condition has to be satisfied. So this can be written as psi square equal to 1. So this will be 2 by a sine square n pi by a to x equal to 1. So this is equal to 2 by a sine square n pi by a into x sine square q plus half into pi. So this will be pi cancel out. Your q value is from 0 to infinity and x can be written as twice of q plus 2 divided by a. So this is the point where probability of the wave of finding the particle will be maximum. Okay, now we'll see for different quantum numbers where the probability will be maximum. So for n equal to 1, x will be twice of q plus 1 divided by 2 into a. So q value may be vary from 0 to infinity. For 0, it will be a by 2. For n equal to 2, x will be 2q by 4 into a. Okay, so for when q equal to 0, this x value will be a by 4. When it is 1, it will be 3a by 4. So these are the points where probability is maximum. So let's draw the graph of probability versus dimension of the box. Suppose this is the one-dimensional box. Okay, if we put this way the probability and this way the dimension, this point is 0, this point is a. For n equal to 1, at a by 2, this is the a by 2, probability is maximum is the maximum probability. Suppose this is p equal to 1. Similarly, for n equal to 2, for second quantum number n equal to 2, we find that the probability is maximum for a by 4, and 3a by 4. Then the probability graph will be somewhat like this. Okay, so this is the required graph. So if you know these things, you can easily solve the problem from this portion of quantum mechanics. In the later video, we'll discuss some problems and related questions from this part. So guys, if you have any doubt, please let me know in the comment section below, and subscribe our channels for more videos on chemistry based on CSIR net and GATE as well, and press the bell icon for instant notification. Thank you.